So this video is going to go over acids and bases and some basic definitions. And in particular, we're going to be looking at Bronsted-Lowry acids and bases. And you may recall that when we think about a Bronsted-Lowry acid and base, these are going to be acids and bases that are concerned with the movement of protons, or H pluses. And we call these protons because a hydrogen atom has one proton and one electron. So if we're H plus, we've lost the electron, and the only thing left is a proton. So chemists will call H plus and proton, use those terms interchangeably. So when we think about these, a Bronsted-Lowry acid is going to be a species that's going to donate a proton. So we call it an H plus donor. It's the molecule that's going to give up an H plus. And our base then is the molecule that's going to be the H plus acceptor. So the molecule that's going to gain an H plus in a chemical reaction. So what we have shown below is a reaction between hydrochloric acid, HCl, plus water going to our hydronium ion, NCl minus. And when we look at this molecule, we can look at it and see that the hydrogen bound to the chloride here ends up bound to our oxygen here. And so when we look at this, we can label HCl is our acid and water is our base, because water was the molecule that gained the proton. It's also important to point out that anytime an acid reacts with water, we're going to form our H3O plus ion, which is the hydronium ion. And as we'll see in the future, the more hydronium, the higher the H3O plus concentration, the more acidic a solution is. And we'll learn about that a little bit more later when we talk about pH. So those are our basic definitions of Bronsted-Lowry acids and bases. But it's important that when we look at these, we're able to look at a molecule and to identify what is an acid and what is a base by the molecular structure. And so we'll start off looking at an acid and say, how can we learn to recognize what is going to be an acid? And if you think about the central feature, acids donate an H plus. So the first thing we need in a molecule is to have a hydrogen, right? If there's no hydrogens, we can't be a Bronsted-Lowry acid. And the second thing that's going to make it easier to donate the H plus is we're going to look for molecules with weak bonds to hydrogen. So anytime we're able to weaken our bond to a hydrogen, that's going to make it easier to break that bond and for that molecule to give up a proton. And so when do we see this? And for our purposes in this course, we can really think about having two general classes of acids. If you go on in chemistry, you'll learn about a lot more, but this is a good way to start out organizing them. And the first class of an acid is when H plus is bonded to a highly electronegative element, such as a halogen. This is usually group 16, group 17 elements. And what's happening here, if we think about this, we can draw a simplistic structure, A bound to H, where in this case, our A is just some electronegative element. And so what's happening is if we have a highly electronegative element, then this molecule becomes very polar. And this element here is pulling all the electron density in this bond towards itself. And what starts to happen is it starts to unequally share these electrons, and it removes the electron density from that hydrogen, making it start to look almost ionic. So this electronegative atom removes our electron density from the hydrogen, making it easier for a base to pluck off. Right. And some examples of this, we can look at a couple of examples. Examples are, again, it's usually the group 17 elements, so hydrochloric acid, hydrofluoric acid, hydrobromic acid, or hydroiodic acid would be good examples of these. The second class, when we think about acids, are what are known as oxoacids. And oxoacids are where we have really this OH group of a molecule. And that OH group is bonded to a central atom and that central atom has double bonded oxygens attached. So what do we mean by that? If we draw some structures here to get our point across, when we think about this, we might think about, move this down a little bit, a molecule C double bond O, O, H. And in this case, we can draw acetic acid. And when we look at this, it's this portion of the molecule we want to be looking at. So as soon as you see an OH, but this O is bounded to a carbon with a double bonded oxygen, then this proton will be acidic. And this is a very similar argument to what's happening above, is we can think about this oxygen is removing electron density from that carbon, putting a partial positive on this carbon. And that's what's that going to do is it's going to help this oxygen, which was already pulling electron density away from this hydrogen, make pull even bigger. It's an even stronger pull because now it's adjacent to this positively charged carbon, helping to remove that electron density and weaken that bond to a hydrogen. All right, so another example of this type of molecule would be nitric acid, and nitric acid would look like this. And again, we have the same feature here. We have this OH bonded to a nitrogen, double bonded to an oxygen, and so this hydrogen is going to be acidic here. Okay. So those are examples of our acids. So for our bases, so a base accepts an H+. So what we need to accept an H+ is we need a lone pair of electrons, because it's really this lone pair of electrons that's going to accept the H+. And often, although not always, these have a negative charge. But that's not always the case, but often we're going to see that. And we're going to actually go over 3 types. All right. So the first one is a metal hydroxide. Okay, and hydroxide, if you recall, is this ion here. So here's hydroxide. And one of the things to take note is hydroxide is really our measure of how basic a solution is. So the higher, the greater the hydroxide concentration, the more basic the solution. So anything that's going to put a hydroxide in solution is going to be basic. And with a metal hydroxide, if you take any metal hydroxide, so where M is just metal, hydroxide as a solid, if we dissolve this in water, we're going to get metal plus aqueous plus OH minus aqueous. So metal hydroxides will directly put hydroxide into solution. And we can see this in different types of metals. I've just drawn a generic metal hydroxide, but we could also imagine having something like sodium hydroxide or calcium hydroxide, which would actually put 2 hydroxides for every calcium hydroxide in water and other molecules like that. The second main class of base that we should be aware of are what I'm just going to describe as ammonia-like molecules. So ammonia is NH3, or drawn out, we have nitrogen with a lone pair and then 3 bonds to a hydrogen. And so this is going to be a fairly good base for us. And so what we're looking for is nitrogen with a lone pair and 3 bonds. Anytime you see this, it's a good chance that we're dealing with a base. So another example of this would be other molecules. So here would be another case where we have a actually cyclic structure. The nitrogen, double bond, double bond, double bond, and then hydrogens all around. Lone pair on nitrogen. So in this molecule, this nitrogen here is going to be basic, and that's going to be able to grab a proton from an acid. And then our third class, which we're going to have to talk about more, but I'll write down for now, and then we'll talk about and define this a little bit later, is the conjugate base to a weak acid. And so that definition is actually based on an acid, but anytime we have a weak acid, its conjugate base will be a weak base. Okay? In the next lecture, we'll talk a little bit more about conjugate acid-base pairs and strong versus weak acids and bases. Thank you.